Okay, now let's discuss ways in which we can quantify these energies that it takes to overcome the intermolecular forces from a liquid going to gas or a solid going to liquid or any phase transition. Now, the energy that it takes to overcome these intermolecular forces depends on the transition. So if we're talking about going from the liquid to the gas phase, and of course we call that evaporating, boiling, and from here on out vaporization, what we have is a thermodynamic quantity known as the heat of vaporization. And as you'll find out in Gen Chem 2, heat of vaporization is a state function, so we look at the change in heat of vaporization or enthalpy of vaporization. Okay? It turns out that these values we listed here for water, it takes 40.7 kilojoules per mole of water to transition from the liquid to the gas phase. Now all of that energy is going into breaking those intermolecular forces or overcoming them. Okay? When you do the opposite transition, gas to liquid, refer to that as condensation, you actually transfer 40.7 kilojoules of energy per mole of water to the surroundings, and that's why you get a negative value there. Solid to liquid, we refer to that melting or fusion. We can discuss the heat of fusion, or the energy that it takes to undergo these transitions, or liquid to solid. Okay, and it turns out it doesn't take as much energy to go from the solid to liquid phase. Of course, we're not completely overcoming the intermolecular forces, we're just giving them sort of a little bit of room to wiggle around. And it only takes 6.02 kilojoules per mole of water. And if you go from the liquid to solid phase, you freeze, you actually transfer 6.02 kilojoules per mole to the surroundings. Of course, there's other transitions we can go. We can go straight from the solid to the gas phase, and we refer to that as sublimation. Taking a look at that previously, of course, dry ice, carbon dioxide sublimes. Or if you go from the gas to the solid phase, we refer to that as deposition. Okay? Additionally, we also have to think about how much energy it takes just to warm a substance, whether it be water or any other substance. And that amount of energy that it takes to raise the temperature of, say, we'll just keep it simple, for water, depends on, of course, how much water you have. So we will get units of joules energy per mass degrees Celsius, and that's referred to as specific heat. Now, each of these transitions, prior to transitioning from, say, the solid phase to liquid phase, if you're below zero, you have to increase the temperature. So it takes 2.09 joules per gram degree Celsius to increase the temperature of solid water. Here's the ice melting heat of fusion, 6.02 kilojoules per mole. It turns out that when water is in the liquid phase, it takes 4.18 joules to raise 1 gram of the substance 1 degree Celsius. Liquid water, when you're vaporizing it, excuse me, that is down here at 3. When you're vaporizing water, going from the liquid phase at 100 degrees Celsius to the gaseous phase, it takes 40.7 kilojoules per mole, as we discussed. And if you want to raise the temperature of steam, you're going to need 2.01 joules per gram of steam to raise it 1 degree Celsius. Okay, so using any one of these values, depending on what you're doing, either raising the temperature of ice, transitioning from solid to liquid, raising the temperature of liquid, transitioning from liquid to gas, or raising the temperature of gas, you're going to use any of these values. Okay. Now to do so, you can utilize some simple heat equations. Okay. So when you want to change the temperature, raise or lower, you're going to use the equation Q, which is, the energy, heat energy, equals mass times the specific heat, which again is different for each phase of water, times the amount of the degrees in centigrade that you want to change, or the delta T. Okay? When you want to do a phase transition, you're going to calculate the amount of heat you need by multiplying the number of moles times the heat of fusion or heat of vaporization. Okay, so those will be your two equations that you need when you're determining how much energy it takes to do some process for a substance. Now we're going to do examples with water, but the same calculations would hold true for any substance. They would just have different values for specific heat or delta H. Okay, so let's do one. Let's calculate the energy needed to heat 25 grams of water from negative 10 degrees Celsius to 60 degrees Celsius. Okay, so let's think about the calculations that we're going to need to do. Okay, we're going to take negative 10 degrees Celsius water. It's in the solid phase. The first thing we need to do is heat it up to 0 degrees Celsius, and it's still in the solid phase. Okay. Then what you're going to do is you're going to calculate the energy needed to take water at 0 degrees Celsius and convert it to liquid phase. And of course that takes some amount of energy. And then because 60 degrees is still in liquid phase, we're going to calculate how much energy it takes to raise the temperature of the water to 60 degrees Celsius. And that's still in the liquid phase. So all of these values take some amount of energy, and sum of that energy will equal our answer. Okay, so let's go after number one. Let's calculate the temperature, or the amount of energy it takes to raise the temperature of water from negative 10 to 0. So we're going to use our Q equals mc delta T. We know that our mass is 25.0 grams. Our specific heat is 4.18. Excuse me, that's for liquid water I was looking at. So this is solid water, or ice. So this would be 2.09 joules per gram degrees Celsius. We're going to multiply that by the delta T. Now delta T is always calculated as temperature final minus temperature initial. So our final temperature that we want is 0 degrees Celsius. Our initial temperature is negative 10 degrees Celsius. So that's going to give us 10 degrees Celsius for a change in temperature. And if you throw that in your calculator, you get 522 joules. Okay. Our second, so we've done there. Our second calculation will involve the energy needed to transition from solid to liquid. Okay, so we're going to need our Q equals N times delta H. Okay, now 25 degrees or 25 grams of water. We're going to calculate how many moles that is. So 25.0 grams times 1 mole over, calculate the molar mass of water, which is around 18.0 grams. And what you will get is 1.39 moles times delta H, which is for the transition from solid to liquid, is 6.02 kilojoules per mole. Okay, so when you do that in your calculator, you are going to get a value of 8.36 kilojoules. Okay, so here you have to be careful. All of your specific heats constants are given in joules. All of our enthalpies, or delta H's, are given in kilojoules. So when you calculate your final answer, you're always going to need to convert one to the other, ensure that you have the same units. Okay, so we did that calculation. Now we're after the third calculation. How much energy does it take to heat the water from 0 degrees Celsius to 60 degrees Celsius? So we're going to go back to our mc delta T equation. We still have 25.0 grams of water. The specific heat of liquid water is 4.18 joules per gram degrees Celsius times our change in temperature, which will be a final 60 minus our initial 0, or 60 degrees Celsius. and that gives us a value of 6,270 joules. So now we just need to sum the total of them. So kilojoules or joules, it doesn't matter. Since we have only one in kilojoules, let's convert that into joules. So that's going to be 522 joules plus 8.36 times 10 to the third joules plus 6,270 joules. And that is going to give us a value of 15,200 joules, or 15.2 kilojoules if you kept it in kilojoules. Okay, another convenient way to look at the transitions between liquids, solids, and gases is to